Carrier hermetic centrifugal chillers, like all of our products, are made to last. Our reputation is built on that fact. But as good as we make them, these units are sophisticated pressurized machines, and you can't just hook them up and forget them. If you care diligently for your chiller, you will be rewarded not only by having relatively few problems over the years, but you'll also be saving yourself a lot of money on major repair bills you would otherwise have to pay. So, the more you know about our machines, the better it is for all of us. This program was designed specifically for owners, machine operators, and those who maintain centrifugal chillers. In this program, we will cover machine familiarization, the refrigeration cycle, chiller controls, chiller operation, refrigerant management, maintenance, and safety. When you've finished, you should have a good understanding of how the chiller works and what you need to do to ensure continued trouble-free operation. 19 series machines such as the XR, the XL, the XRT, and the EX vary in size and tonnage, but are similar in operation. So, for simplicity then, let's just consider the 19XR hermetic centrifugal chiller. The chiller has three main parts: the cooler, the condenser, and the compressor. The compressor is mounted on top of the cooler. The cooler is really just a big tank with a lot of tubes running through it. The chilled water that circulates through your building runs through the tubes, giving up the heat it gained in the building to the HFC 134A refrigerant that is outside the tubes. When the cooled water leaves the cooler, it's ready to recirculate to the building and absorb more heat. The refrigerant outside the tubes in the cooler is in liquid form, and as it absorbs heat from the water in the tubes, some of it vaporizes and flows upward into the compressor. The compressor acts as a pump, causing the refrigerant to circulate through the chiller. In it, the vapor is compressed and leaves the compressor at a higher temperature and pressure. Now, the heat that passed from the building to the water and into the refrigerant must be removed, and that happens in the condenser. The condenser is another big tank with tubes running through it. Like the cooler, the refrigerant is on the outside of the tubes, and the cool condenser water runs through the tubes. The condenser water absorbs heat from the refrigerant and then circulates to a cooling tower, usually on the roof of the building, where it rejects the heat to the atmosphere. As the refrigerant is cooled, it condenses from a hot gas to a warm liquid, which is then fed to the cooler to repeat the whole process. The compressor contains an external oil pump driven by its own electric motor. It is mounted in the transmission oil sump and circulates oil to the main bearings and transmission gears. The crankcase contains an electric heater to keep the oil warm when the compressor is not running, to prevent the oil from absorbing refrigerant, which would dilute it. An external oil cooler is provided to cool the oil when the compressor is running. Oil from the pump discharge passes through the oil pump motor and serves as a coolant. Oil pressure is regulated by a relief valve that's located internally. The valve relieves the pump discharge back into the oil sump, maintaining proper oil system pressure. Pressurized oil then passes from the pump motor housing and into the filter chamber via some external piping. After being filtered, the oil is piped to the external oil cooler. The pressurized oil flows to the transmission assembly where it feeds two lines. One line supplies oil to the high-speed thrust-bearing assembly and lubricates the gears. The other line supplies the low-speed shaft bearings. From there, the oil is channeled to the high-speed shaft bearing nearest the pinion. The oil then drains to a sump at the base of the compressor housing. The chiller control system is called the PIC, for Product Integrated Control. Your chiller may be equipped with either PIC 1 or PIC 2 controls. The PIC 2 controls operate very much like the PIC 1, but contain some additional features. These include visual display and processor combined into one board, CVC. All inputs and outputs combined into one board, CCM. Motor protection and starter control provided by the ISM. The PIC controls the operation of the chiller by monitoring all operating conditions. The PIC can diagnose a problem and let the operator know what the problem is and what to check. It promptly positions the guide vanes to maintain leaving chilled water temperature. It can interface with auxiliary equipment such as pumps and cooling tower fans to turn them on or off when required. It continually checks all the safeties to prevent any unsafe operating condition. It also regulates the oil heater while the compressor is off. The PIC can interface with the Carrier Comfort Network, or CCN, if desired. It can communicate with other PIC-equipped chillers and other CCN devices. The PIC consists of three major components. These are the control center, the power panel, and the starter cabinet. Mounted in the control center is a device called a LID, Local Interface Device, which allows the operator to start and stop the chiller, read data, and enter operating parameters. The starters for the compressor and other motors are located in the starter cabinet next to the compressor or in a freestanding cabinet. The Control Center module communicates with the Starter Management module. Amperage, voltage, and operating information is relayed between the two modules. This operating information can be displayed on the lid by pushing the status function soft key. Now let's take a closer look at what goes on inside your chiller. Centrifugal compressors are non-positive displacement compressors. These compressors obtain compression without reducing the internal volume of the compression chamber. They are suitable for compressing large amounts of refrigerant and normally are used in very large capacity cooling systems. A centrifugal compressor is a relatively simple mechanism. Its basic components are an impeller, a diffuser, and a volute casing. Large tonnage centrifugal compressors may have two or more impellers or stages in the same casing. Centrifugal compressors are usually driven by hermetic electric motors. The impeller is the heart of the centrifugal compressor. It is a rotating circular disc with curved blades that is driven at high rotational speed by the electric motor. As the impeller rotates, it moves the refrigerant vapor from its suction opening in the center to its outer edge by centrifugal force. The vapor enters the suction at a relatively low velocity and leaves the outer edge of the impeller at a high velocity. In other words, the impeller transfers its rotational energy to the vapor. However, high velocity is not high pressure. In order to get a pressure increase, or compression, the vapor must be slowed down to convert its velocity pressure to static pressure. This is accomplished in the diffuser. As the high-velocity vapor moves radially outward through the diffuser, the flow area increases, slowing the vapor and increasing the pressure. Some diffusers have vanes or pipes which change the flow direction and further slow the vapor. Finally, the volute-shaped casing collects the slow-moving high-pressure vapor from around the diffuser and conveys it to the discharge connection of the compressor. Inlet guide vanes are used to control the capacity of the centrifugal compressor. These are movable vanes located in the suction opening. When they are turned fully open, the compressor produces its full cooling capacity. As they are closed, they reduce the amount of refrigerant flow through the compressor and thus reduce the capacity of the refrigeration cycle. The basic centrifugal refrigeration cycle operates much like the positive displacement compressor cycle, with some exceptions. Our example is a centrifugal water chiller with a water-cooled condenser. The system is charged with HFC 134A, a high-pressure refrigerant. The chilled water leaves the evaporator, known as a cooler, at 45 degrees Fahrenheit, and the cooling tower water enters the condenser at 85 degrees Fahrenheit. Refrigerant pressures and associated saturation temperatures can vary widely based on the type of tubes in the heat exchanger, whether a brine or freshwater solution is used, the pass arrangement on the heat exchanger, and the water flow rate. These values are normally found on the chiller design data specification sheets. The pressures and temperatures shown in this example are typical for a chiller sold today, but variations do exist. We will start where the liquid refrigerant flows into the evaporator. This is a flooded shell and tube heat exchanger with the chilled water in the tubes and the refrigerant liquid in the shell around the tubes. It is called flooded because the liquid refrigerant covers the chilled water tubes. The centrifugal compressor continuously draws refrigerant vapor from the evaporator, or cooler, maintaining the evaporator pressure at 39.0 psig, which corresponds to a saturated evaporation temperature of 44 degrees Fahrenheit. The 44-degree liquid refrigerant picks up heat from the chilled water flowing through the tubes, causing the refrigerant to evaporate and cooling the chilled water from 55 degrees Fahrenheit to 45 degrees. The entering chilled water temperature is not controlled by the chiller. It is the air handlers or load supply that will send out the water at a temperature that's based on the load in the building. The 55-degree Fahrenheit temperature is the full load entering water temperature that the machine will be able to pull down to 45 degrees Fahrenheit at the designed condenser water temperature. The chilled water is distributed to fan coils which cool, dehumidify, and filter the indoor air. There is very little superheat in the vapor leaving the flooded evaporator. The refrigerant vapor is drawn from the cooler by the centrifugal compressor at a rate set by the inlet guide vanes, compressed to a pressure of about 120 psig, and discharged into the condenser. The compression process adds heat to the compressed vapor, raising its temperature to about 120 degrees Fahrenheit. This temperature will change based on load, refrigerant charge, or non-condensables in the machine. The water-cooled condenser is a shell and tube heat exchanger similar to the evaporator. Cooling tower water at 85 degrees Fahrenheit flows through the tubes, removing heat from the refrigerant vapor, causing it to condense on the outside of the tubes. The saturated condensing temperature of the refrigerant vapor is 98 degrees Fahrenheit, corresponding to the pressure of 120 psig. The condensed refrigerant liquid drains to the bottom of the shell, where it passes through orifices into the flask chamber. Since the chamber is at a lower pressure, part of the liquid refrigerant flashes to vapor, thereby cooling the remaining liquid. The cycle is completed as the cooled liquid refrigerant flows through a metering device and returns to the evaporator. As shown, the float valve controls the flow of liquid refrigerant between the condenser pressure of 120 psig and the evaporator pressure of 39.0 psig. The float maintains a refrigerant level in the float chamber, which provides a positive liquid seal and prevents condenser vapor from blowing directly into the evaporator. When the liquid passes through the metering device, some of it flashes to a vapor in the lower pressure on the evaporator side. In flashing, it removes heat from the remaining liquid, lowering its temperature to 44 degrees Fahrenheit. The cold liquid then flows into the evaporator shell, where the cycle begins again. You can see that proper operation of the chiller depends on having the chilled water and condenser water temperatures and flow rates correct. You should be aware of the conditions the machine was designed to operate under, which includes water temperatures, pressures, and so on. These are just some of the things you will be concerned with in monitoring the operation of your system. Now, stop the tape and go to your workbook. Now let's take a closer look at the controls. The lid is the device that lets you communicate with the controls. It contains a liquid crystal display and 4 keys used for starting the chiller and accessing the control software. To the left of the display is the alarm light, which flashes when abnormal conditions occur. Below the alarm light is the stop button, which, if depressed for at least 1 second, will cause the chiller to shut down. Unless another screen has been manually called up, the lid continuously displays a default screen containing a lot of useful information. Things like date, time, operating or shutdown mode, status messages, alarm messages, and 9 of the most important operating temperatures and pressures. You will quickly learn the normal values of these points, and will be able to confirm that operating conditions are normal just by checking the lid screen periodically. And if the chiller is not holding the load conditions, or is shut down when it should be running, the lid screen will help identify what's wrong. If an alarm has occurred, the lid screen will display a message identifying the cause of the shutdown. The lid can be used to access considerable other operating data as well. The function of the keys below the display is identified in the bottom line of the display. When the default screen is displayed, the last key at the right is called Menu, and depressing it reassigns the function of all 4 keys. They now become Status, Schedule, Setpoint, and Service, which are the 4 major divisions of the software. Depressing the status key allows you to select any one of 3 screens that contain additional operational data. Of course, while you're doing this, the default screen disappears, but it will return again as soon as the lid keys have been idle for 5 minutes. The rest of the accessible software is used for configuring the controls for specific applications, setting up operating schedules, entering set points, and so on. We won't go into all that here. If you want to understand the operation and use of the entire control system, a package training program is available for that purpose. Now we should talk a little bit about alarms and alerts. An alert is an abnormal condition that generates a warning message. It might delay startup, but is not serious enough to warrant shutdown of an operating chiller. The message is displayed at the top left corner of the default screen, and if the point that is in alert is one of those displayed on the default screen, that point will be flashing on and off. Think of an alert as an early warning of conditions that might become serious if not corrected. An alarm is an abnormal condition serious enough to prevent startup or to cause automatic shutdown of an operating chiller. Whenever an alarm occurs, the lid default screen will freeze and display the condition of the chiller at the time of the alarm. This is useful for troubleshooting. Be sure to record the data before pressing any of the soft keys. The alarm light at the left of the display will activate whenever an alarm exists to call attention to the condition. When the problem has been corrected, the chiller can be restarted by first pressing the reset key and then pressing either the local or CCN key, depending on whether the chiller is under local or remote control. Your chiller is well protected by the PIC controls. Here are just some of the points that are monitored by the controls: compressor motor temperature, bearing temperature, oil temperature, oil pressure, discharge gas temperature, cooler pressure and condenser pressure, water temperatures entering and leaving the cooler and entering and leaving the condenser, and compressor motor amps and volts. If any of these points should go beyond safe operating limits, an alert or alarm is generated, and the chiller is automatically shut down if the condition becomes serious. The controls even automatically check the temperature and pressure sensors to ensure that the sensors are not faulty. Now it's time to look at the startup and shutdown sequences for your chiller. There are two modes of control, local and CCN, and a start key is assigned to each mode when the default screen is displayed. Local control is just what it sounds like. Total control of the chiller is at the local site. CCN control exists when the local chiller controls are connected to a carrier comfort network system or building supervisor, where control of the local chiller may be at a remote location. Using the CCN key allows the chiller to respond to network commands. There are several things that need checking before you push the start key, either local or CCN, to start the machine. Is power turned on to the main starter, the oil pump starter, the water pumps, the tower fans, the oil heater and machine controls? Has proper water flow in the cooling tower circuit been confirmed? Has the chilled water circuit been checked out for proper flow? Is there oil in the compressor oil reservoir sight glass? Whether the machine is on or off, you should always see oil there. For our example, we will assume your chiller is a standalone installation subject only to local control. Depressing the local key allows the chiller to start, run, and shut down in response to commands from the control system supplied with your chiller. Several conditions must be met before the chiller can start. First, the present time must fall within the occupied time period. Occupied time is the time period each day of the week when you want the chiller to maintain comfort conditions in the building. Any time not designated as occupied is considered unoccupied, and the chiller normally does not operate during unoccupied conditions. Occupied times are usually configured at the time of initial startup and checkout of the chiller. If it is desired to operate the chiller during an unoccupied period, it is possible to override the controls at the lid for up to 4 hours. Instructions for doing so will be found in the startup, operation, and maintenance instructions provided with the chiller. Once the local key is depressed and an occupied time period exists, the chiller begins a startup sequence, where it first checks to see if there are any alarms or alerts in effect. If there are none, it starts the chilled water pump and condenser water pump, cooling tower fan, and confirms water flow. The chilled water temperature is then compared to the set point to determine if the chilled water needs cooling. The set point is the desired temperature of the chilled water as it circulates through the building, and is normally configured at the time of initial startup and checkout. If the chilled water temperature is above set point, the sequence continues and the compressor guide vanes are checked for closure. If the guide vanes are closed, the oil pump is started and lube oil pressure confirmed. After the local key has been pressed, it will take a minute or more for the startup sequence routine to start the compressor. Pay attention to what a normal start sounds like so that you will be better able to detect a problem if anything unusual develops in the future. Once the compressor is running, the controls will operate the inlet guide vanes to provide the proper compressor capacity required by the building, and will manage the operation of optional features such as temperature reset or demand limit. The compressor will shut down when the chilled water temperature drops below set point. This is called a recycle shutdown, or when an occupied time period expires, or when the stop key is depressed for at least 1 second, or when an alarm condition occurs. When any of these conditions occur, the compressor is shut down and the guide vanes are closed. The oil pump is shut off 1 minute after the compressor stops, and the condenser water pump is shut off when the condenser pressure drops to a predetermined level. The chilled water pump remains operating during a recycle shutdown to monitor the chilled water temperature for an increasing load. Otherwise, it is shut off at the same time as the oil pump. Remember that shutting the compressor down manually requires only that the stop key be depressed for at least 1 second. Also remember that the controls will not allow a restart until 15 minutes after the last startup and 1 minute after the last shutdown. We said earlier that if a safety shutdown occurs, an alarm condition, the reset key must be depressed in order to restart the machine. An alarm condition is a serious situation, and there may be a risk of serious damage to the chiller if the problem is not properly analyzed and corrected before resuming operation. Therefore, unless you have corrected the cause, don't reset and restart from an alarm condition. If it's a serious problem, have a carrier technician evaluate the situation and ensure that the problem has been corrected before restarting. One of the operator's most important jobs is to spot any problems before they become serious. So the machine's operating characteristics should be checked and recorded at least once a day, preferably at the same time each day on an operating log sheet. The PIC controls make this very easy to do because most of the important data can be read directly from the default screen. A typical log sheet will have provision for refrigerant temperatures and pressures, chilled water temperatures and pressures, condenser water temperatures and pressures, compressor bearing temperature and compressor oil pressure and temperature, and motor amps. This information can be obtained from the lid default and status screens. Be sure to always indicate on the log sheet any service or maintenance performed, including quantities of any oil or refrigerant added or removed. Here are some typical temperature and pressure ranges for a typical comfort cooling application. The chilled water leaving the cooler should be close to the chilled water set point, and the return water should be about 10 degrees above the leaving water temperature at full load conditions. The saturated temperature of the refrigerant in the cooler will vary with design conditions, but will be typically 34 to 45 degrees Fahrenheit. Condenser cooling water is normally in a cooling tower circuit and will typically enter the condenser around 85 degrees Fahrenheit and leave at about 95 degrees Fahrenheit at full load conditions. Water entering the condenser should never be less than 65 degrees Fahrenheit, or there will be insufficient head pressure for proper operation. Entering condenser water should be less than design full load temperature at less than full load conditions, and the saturated temperature of the refrigerant in the condenser will range from 60 to 105 degrees Fahrenheit, depending on design conditions. Discharge oil pressure should be 18 to 30 psi above the oil sump pressure. The oil in the compressor sump should be 140 to 150 degrees Fahrenheit. The bearing oil return temperature is okay between 120 and 165 degrees Fahrenheit. The oil level in the sight glass should be visible anywhere in one of the two sight glasses, both when running and when shut down. Motor amperage is in percent of motor current that's being used. Always refer to the equipment's original design data for full load operating conditions. Now, about your daily log sheet. Don't just take readings. When you check the temperatures and pressures, you must also know what these numbers mean. They may signal trouble, and it's up to the operator to notice it. After you take the complete set of log readings, compare the readings with the design or startup set of readings. If there are any significant differences, you need to find out why and correct any problems that may exist. Now we come to something that every owner of air conditioning equipment must face: refrigerant management. 10 or 15 years ago, refrigerant management was pretty simple. When you needed to open up a system for maintenance or repair, you stored or blew off the refrigerant, and when you closed up the system, you charged in whatever new refrigerant was needed. If you needed more refrigerant, you sent somebody out to buy it. There was no penalty, except for the refrigerant cost, for leaks, and nobody knew or cared much about ozone depletion. Now, production of the chlorinated HCFC refrigerants is being phased out, and the CFCs are already gone. Venting of refrigerants is no longer allowed, and stiff penalties await those who violate the U.S. Clean Air Act. Strict regulations cover the recovering, recycling, and reclaiming of refrigerants. The ASHRAE 15-1994 Safety Code contains new requirements for machinery rooms. And of course, the EPA requires that anyone who handles refrigerant must be certified. Dealing with all this is no simple task. It is essential that owners create and maintain a plan that will enable them to continue to provide cooling for their buildings while complying with all regulations. Among other things, the plan must take into account refrigerant availability and define the risks and actions to be taken in the event of an accidental spill. A primary goal of the plan is to ultimately be free of all equipment using chlorinated refrigerants. With your new 19XR that uses HFC 134A, the plan will be quite straightforward. Future supplies of the refrigerant are assured, and if the chiller has isolation valves, the operating charge can be stored in the condenser or evaporator using the optional pump-out unit when service is required. The refrigerant plan will mainly address things like complying with regulations, proper record-keeping, leak detection, and steps to reduce risk of accidental emissions. For those who have low-pressure CFC chillers, the waters are considerably muddier. A continued supply of refrigerant will depend on recycling and reclaiming, and will undoubtedly become increasingly costly. Leak detection and prevention are more difficult than with a high-pressure chiller, and the penalties for emissions of CFCs are more severe. Leak prevention becomes extremely important, not only because of environmental considerations, but because of limited availability of replacement refrigerant. The owner of a low-pressure chiller ultimately faces three choices: replacing the chiller, converting the chiller to an HFC refrigerant, or containment of the CFC refrigerant. Containment means taking all reasonable steps to ensure that refrigerant is not lost to the atmosphere. Conversion of a low-pressure chiller to a different refrigerant can cost almost as much as a new chiller, so it may not be a good choice. If the machine is relatively old, replacement may be the best approach. If it's relatively new and is in good condition, containment will probably be the most economical approach. There are many products available today that serve the containment task. They include refrigerant transfer and storage equipment, leak detection devices, relief valve backup for fraggable disks, pressurization equipment for shutdown conditions, high-efficiency purge systems, refrigerant recovery systems, and others. Fortunately, you are not alone. Carrier has several publications which address all of these issues in depth. These provide building management people with guidance in identifying the problems, making the convert, contain, replace decisions, and creating a manageable plan. They identify a wide variety of containment equipment and replacement equipment, and help in determining actions needed to comply with EPA and ASHRAE requirements. The refrigerant plan will identify what containment equipment will be used, when the chiller is due for replacement, and how personnel will be trained in the proper operation and handling of the containment equipment and processes. We urge you to ask your Carrier representative for any of this information. Now, stop the tape and go to your workbook. Now we need to talk about maintenance. The sad truth is that when our technicians are called to fix machines with major problems, they often find that these problems are due to poor maintenance. If you let the machine run itself and wait for problems to develop, problems will indeed develop. But if you maintain it well, your chiller should give you many years of continuous duty. It's always more costly and disruptive to deal with an emergency breakdown than to provide maintenance on a planned schedule. The key to proper maintenance is a good preventive maintenance program. Such a program identifies what is to be done and when it is to be done. A successful program requires that the work be done on time, proper procedures are used, accurate records are maintained that are easily accessible by those that need them. Fortunately, Carrier offers an extremely versatile selection of inspection, monitoring, maintenance, and repair services, allowing the owner to determine for himself just how much of the maintenance responsibility he wishes to assume. Contracts can be tailored to include just the services desired, which can range from basic equipment monitoring to complete multi-year planned maintenance programs. Contact your local Carrier Building Systems and Services office for details of these services. The need for good maintenance goes beyond just avoidance of problems. If heat exchanger tubes become fouled or water flow rates or temperatures are not proper, operating efficiency can become seriously affected. For instance, if condenser tube fouling causes a 5% increase in condensing temperature, chiller capacity will be reduced and the power requirements will increase by 11.5%. Tube cleanliness, then, is of great importance. Which brings us to water treatment. Condenser cooling water is usually an open system served by a cooling tower. Because the water is in contact with air, scale, corrosion, and algae can quickly build up on the inside of the tubes. This is called fouling, and it can greatly reduce heat transfer, causing increased condensing temperatures. To limit fouling, condenser water must be treated. Corrosion can produce pits that penetrate the tube walls, causing internal machine contamination and requiring replacement of some or all the tubes. A water treatment specialist should be consulted to determine the proper treatment for local conditions and to set up a treatment program. It's extremely important to carry out all maintenance requirements for the water treatment and for the cooling tower itself. Even if you contract out the majority of maintenance work, you still need to understand what it is that needs to be done. After all, it's your equipment. The better you understand it and the better care you give it, the better it will serve you. So let's look at some of the things that need to happen. On a daily basis, we've already covered the operating conditions that should be read, entered in your log, and reviewed. In addition to that, you need to be listening for any unusual sounds or vibration, and you must be alert for the possibility of refrigerant leaks. If you have permanent leak detection equipment installed, be sure to monitor it and check to ensure it's working properly. Small leaks in high-pressure machines are sometimes visible before they are detected by instrumentation, because a small amount of oil may accumulate at the leak site. If the annual leakage rate for the entire chiller is greater than 10% of the total operating charge, the leak should be repaired immediately. If the total leakage rate is less than this, but greater than 1 pound per year, the leak should be marked and repaired during annual maintenance. A new training program for leak testing liquid chillers is now available. Refer to the workbook appendix for ordering information. On a weekly basis, the lubrication system should be checked. Keep your eyes open for oil leaks. Make sure the operating and shutdown oil levels are within the proper range in the sight glass or glasses, and mark these levels so you can tell if you're losing oil. If you do lose oil, make sure you find the leak and have it repaired. If oil must be added, be sure to record the amount added. Oil specifications are important and vary with the refrigerant used, so be sure that all oil you keep on hand meets the manufacturer's specifications. The polyolester oils required for the new refrigerants are very hygroscopic, which means that they will absorb moisture faster and in greater quantities than oil used in the past. This means that any oil stored on site must be sealed from the atmosphere to avoid contamination. Also check to make sure the oil heater is keeping the oil warm when the compressor is shut down. The controls will not allow the compressor to start if the oil is not warm enough. When doing the weekly check, note all water piping for leaks and pipe insulation for damage. Check the chiller thoroughly for signs of rust or damage. Check the thermometer readings in the water circuits against the values displayed on the lid. Also check the water side pressure drops across the cooler and condenser. Check the moisture indicator to ensure that the refrigeration system is adequately dry. And make sure the machine room is neat and clean. Don't let trash accumulate. A clean, well-lit machine room makes system maintenance much easier. Every 3 to 4 months, the chiller should be leak tested, refrigerant charge checked, auxiliary equipment lubricated, control and power wiring checked, starter wiring and contacts inspected, and safety and operating controls tested. Safety controls include flow switches and all pressure switches that may be in use, plus all thermistors and transducers. Thermistors should be checked for open or shorted conditions, and transducer readings at the lid should be checked against calibrated gauge readings. Annual maintenance should be conducted by a Carrier Building Systems and Services technician. Things that need to be done annually include changing the oil filter and refrigerant filter dryer. This is also a good time to send an oil sample to a laboratory for tests to determine the quality of the oil and the possible presence of contaminants. The entire oil charge should be changed after the first year of operation and at least every 5 years thereafter. The condenser tube should be cleaned and the cooler tube should be cleaned and inspected after the first year of operation. Because the chilled water is a closed circuit, the cooler tubes normally will not need cleaning every year, but the first-year inspection will give the technician a chance to see if the water treatment is adequate and to determine a schedule for future cleaning. The condenser temperature sensors should also be checked for scaling and fouling and cleaned if necessary. Other annual maintenance chores include changing the oil reclaim filter in the cooler scavenging line and inspecting relief valves for signs of corrosion, dirt, or leakage. Another important item to check is the compressor motor starter. All wiring connections in the starter should be tight, and the contacts on all starter switchgear should be checked for proper alignment. If the contacts are badly pitted, they should be replaced. On reduced voltage starters, an operational check should be made to determine if the timed interval is proper. On star-delta starters, the mechanical interlock between the start and run contactors should be checked. Other points to check in the motor starter are signs of weakened coils, the insulation on wires, and any formation of rust on air gap surfaces of magnets of the main switchgear. Solid-state starter operation should be checked, and torque and ramp speed should be calibrated. The insulation resistance of the compressor should also be checked. This should include resistance to ground and phase-to-phase winding resistance using an instrument that is correctly sized for the normal operating voltage of the motor. Insulation readings and the temperatures at which they were taken should be made part of the permanent machine records. Going beyond annual maintenance, compressor bearings should be inspected periodically, normally in conjunction with other major maintenance. This operation should also be performed only by experienced personnel. The frequency of inspection will vary with the type of duty of the machine, how critical the application is, the number of hours the machine operates, and under what conditions. If desired, a vibration analysis can be conducted by Carrier and used as a predictor of bearing condition. Two more items that might be included in a long-range maintenance program are cleaning and inspection of the float chamber and eddy current testing of the heat exchanger tubes to check for corrosion, flaws, or weaknesses. The maintenance items we've covered are important, but they are not intended to constitute an all-inclusive list. Remember that if the critical balances of refrigerant, water, oil, and air are maintained, improved efficiency and cost savings will be realized. These result from lower power requirements and the prevention of unexpected major failures. Basically, the aim is to keep the condenser head pressure requirements within equipment specifications. This will result in the lowest possible kilowatt requirements. To achieve this goal, equipment must be continually monitored so that the owner and operator are aware of existing conditions and can take prompt remedial action. Now you know what you need to know to ensure the long life of your Carrier 19XR chiller. The main thing is, if you think your machine might have a problem, it's better to be overcautious and have it checked out than to be sorry later. Before we conclude, there are some safety items you should know about. Fortunately, Carrier has a safety guide for refrigeration and air conditioning equipment to make you aware of safety hazards. There are 3 hazard categories in this guide, which include danger, warning, and caution. There are 3 rules in what we call the danger category. Never shut off or bypass a safety device. Don't start a machine unless a technician ensures that all of the pressure relief devices are properly installed and piped outside the machine room. Never open an isolating knife switch while the machine is operating. Under the warning category, there are these rules. Don't work on high-voltage equipment unless you are a qualified electrician. Don't open refrigerant relief valves. Intentional venting of refrigerant is against the law. In the caution category, avoid stepping on refrigerant lines. They could break or leak, becoming a safety hazard to all in the vicinity. Don't climb on the machine. If you must access an out-of-reach location, use ladders or scaffolding, ensuring that safe practice is always followed. Finally, don't work on electrical components which include the starters, switches, control panel, and the oil heater unless you are positive that all of the power is off and that there are no residual voltages and capacitors or solid-state parts to zap you. If you are going to fix electrical circuits, tag and padlock them open. If you must interrupt your work, make sure that all circuits are off before resuming work. Don't remove any parts while the machine is running or under pressure. When working on electronics, shut off the starters as well as the machine because automatic mechanisms may activate the part you are working on. When replacing any part, be sure to use only material that meets code requirements. Don't vent or empty water boxes unless you are absolutely sure of what you're doing. Don't unscrew water box cover bolts unless you are sure the water box is completely drained. Don't loosen any packing gland nuts unless you are sure the threads are engaged. It's now time for you to put into practice what you have learned. If you would like to learn more about centrifugal chillers, additional training programs or school sessions are available. A 3-day Operating Fundamentals for the 19XL, XR, and XRT, and a 1-week school on centrifugal fundamentals are offered at various times during the year and are especially recommended for those interested in extending their knowledge of the subject.